morning, everyone. Final stretch of supersymmetry. Yeah, so before I start, any urgent questions? No?
I have a question
Yeah.
on yesterday's lecture. In the calculation that we did in the end, I wanted to ask how important was it that we did the calculation on S3? So what was the role of the sphere? Could one do the same calculation on a different manifold?
Yeah, so there are several ingredients that were important for the sphere. So one was this issue of infrared divergences that I mentioned. But even without it, to apply the method of SUSY localization or localization in general, you had to have this kind of a special feature that you have to have an isometry with fixed points. Remember this example on S2? That was kind of the baby version of the problem where things localized on the North Pole and on the South Pole. So that is an ingredient which is important so that you get a reduction from a path integral to an ordinary, matrix integral or just an ordinary integral. So these were the two kind of important reasons to be on a sphere. Was that clear? Since I really didn't really fully do the calculation in front of you, it was not obvious that these ingredients were essential, because essentially I started off from the Lagrangian on S3 with these details that I gave you, and then I gave you this deformation with a parameter t with an explicit action. So it somehow maybe looks like a magic trick, and in a sense it is a little bit. So yeah, I don't know how to do it on flat space is the short answer.
Thank you.
Yeah. All right. So yesterday we ended with the deep fact that this function on S3, or this quantity on S3, is monotonic under RG flow, monotonically decreasing. So some of you ask me, is this proven? How do we know this? Well, by some mathematical standard, nothing in quantum field theory in more than 2 dimensions interacting quantum field theory can be proven, because we don't know what the path integral is. So, the answer is no, it hasn't been proven. But there have been various arguments for this. I think the closest to a proof comes in a paper by Horacio Cassini and collaborators, where they use entanglement entropy methods to what they say is a proof, but again, I don't really know mathematically how rigorous it is. Anyway, this seems to be true. Okay, good. And it's supposed to be valid without SUSY. Although people arrived at it using these SUSY methods, they soon realized that actually this seems to be true without supersymmetry. Okay, so going back to supersymmetry, clearly the free energy on S3 of n equals to 2 QFTs or CFTs depends on the R charges on these quantities Ri. So, in a sense, if you know these are charges, somehow, if someone gives you the numbers, then you can simply use these, whatever, a polylogarithm and blah, 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 and calculate f of S3. Right? Even if it's not an analytically, an explicit analytic calculation, you can evaluate it to an arbitrary accuracy using this special function that I gave you. However, no one told you that finding these numbers is an obvious thing. So very, very simple example. Instead of talking about some abstract things, just to appreciate that this is not always easy, take this case. Okay, so I have two chiral superfields, and I choose this interaction, this superpotential. As usual, the Kähler potential is the canonical one. Whatever, phi I bar. Okay, so choose this. Well, we know that the superpotential has to have R charge 2, so I find R1 plus 2R2 is equal to 2. And in addition, if you have a flavor symmetry, it has to give charge 0 to the superpotential, and so the flavor charges, in this case, you do have a flavor symmetry, and it's this. So from the Lagrangian of the theory, I have these constraints, but the numbers F1 and R1 are free parameters. Okay, so now you have a problem. If you want to compute this, I have a formula, but in the formula, I have a parameter which I don't know. Sorry? Sorry. Did I mess it? I give charge F1 to this, yeah, and F2 to this, and sorry, not one. Did I? Yeah. Sorry. Sorry, yes. Yes. So I have a mistake in my note. Yeah. Anyway, the point is that mathematically you now have a problem. Physically what happens, just to understand a little bit better, when I was explaining what an R symmetry is, I told you that it's a symmetry under which the supercharges are charged. And when I told you what a flavor symmetry is, I told you that this is a symmetry under which the supercharges are not charged. That sounds easy, right? So now, suppose I have both a flavor symmetry and an R symmetry. U1, okay, just to be simple. Then, you may think that you have an R symmetry, R, but actually any combination like that will also be an R symmetry. Because clearly R will obey the definition of an R symmetry. It will charge the generators of supersymmetry because F doesn't give them a charge. So at this point you may be confused. What am I talking here about? So the careful thing to say is that when you do not have conformal symmetry, but you have only supersymmetry, you have an ambiguity in what you call an R symmetry because of what's on the board. Because there's nothing in the SUSY algebra that fixes this constant alpha. However, in the superconformal algebra, there was this very special anticommutator, which in the infinite past, scry minus, which was Monday, I told you it's an important commutator. And now I'll put a hat here just to emphasize that this is a special one. And there was some rotation and so on. So if you have an S supercharge, this anticommutator has a very specific generator on the right-hand side. Okay? So that R hat is called the superconformal R symmetry, and it must be a unique object. So this alpha is in some sense fixed by this. Okay? So in a situation like this one, where you have an RG flow, again, this is one of these examples where it's asymptotically free, and I claim that there's a CFT in the IR. We've done this a few times. So in the UV, this is a free theory. So in some sense, I know everything about it. I don't need these R charges. I can just compute the dimensions of all operators. But then, once you turn this on, I have an RG flow, right? And I go to this IR. And along this RG flow, if you wish, I have a family of R symmetries, like this. So if you wish, this parameter alpha can smoothly change as I undergo this RG flow. But when I hit this point, it has to be fixed. There must be a correct alpha. Okay? Is that picture clear? This argument is crucial. So now you should be asking not what are the R charges, but what are the superconformal R charges? Because what are the R charges is an ambiguous question. It will depend on alpha. And it's good because if you don't have the conformal symmetry, the R charges do not really give you a lot of information because they do not fix the conformal dimensions, right? I don't have conformal invariance. But here, if you know these R charges, at least for some of the multiplets in the spectrum, you completely fix the conformal dimension. So this is valuable information. Okay, so at this point, you can ask, what do I do? And Dan Jafferis told us what to do. He said, just out of pure thought, compute f as a function of the R charges. Right, I have a formula. Compute, this is a general statement. Compute this function. Then the correct superconformal R charges are obtained by maximizing this as a function of Ri. Correct superconformal charges maximize f of s, fs3. This is a deep and important result because now you have a method for, in principle, infinitely many QFTs of this kind to start with a Lagrangian in the ultraviolet with an asymptotically free theory. This applies also with a gauge theory, right? All kinds of examples in principle. Start here, write down the Lagrangian, identify the R symmetry and the flavor symmetries, do this exercise, which is a pure group theory algebra exercise. I have a formula for f of s3, this integral over sigma. Put these numbers into that integral, compute this, find the maximum of this function, and you're done. What does it mean? You're done. You've computed the correct R charges at this point. So you've done the non-perturbative RG flow. So Wilson should be happy. And out of this happiness, also what emerges is that you've computed also the dimension of operators, of some operators, of the short and the semi-short multiplets. So this calculation allows you to compute a part of the spectrum of the CFT exactly and non-perturbatively. No approximation. Okay? Okay. You're not impressed, but you should be. Okay. So now, this is the simplest model I could think of where this operation leads to a non-trivial result. Okay? No gauge field. Yes? What do we call the original theory? The UV theory? That's a boring theory. That's a free theory. So I don't need any fancy stuff to compute in free theories. It's just the weak contraction. Yes, there is no ambiguity. Also, there's no tool to compute alpha. So there's no ambiguity, but there is a lot of ignorance. Yes. So this this ignorance is being solved, if you wish, from the UV data. So if you wish, you know that something must be fixed. And this is a method how to fix it. That's the logic of the argument, yes. I'm not going to go through, so in some sense, Jeffers didn't prove this. Again, the words proof should be carefully used, but he essentially postulated this and then computed in some examples and things were making sense. And then afterwards, other people, since I'm being recorded, I should be careful. Closet, Festuccia, Dumitrescu, Seiberg, and Komargotsky, I think, if I'm not missing names, they kind of went a bit more rigorously into that. And, well, by my standards, I would say they furnish a proof. So, this is true. Okay, so we now have an exercise to do. I encourage you to do it. We have a formula. Now, I don't have a gauge field, so I don't have to do this integral. So I have these two functions, little l, of R1 and R2. I write them down. I ask Mathematica extremize, please, and it happens magically. And here is the answer. So compute fs3 in this model is a function of R1 and R2. Of course, R1 and R2 have to obey a constraint, so it's some kind of a constraint extremization problem. And extremize to find this answer. Delta 1, which is equal to R1. So this is the conformal dimension of the scalar field in the super multiplet phi1, which is equal to the R charge. This is this LB1 multiplet. And it's some number that I don't have a closed form expression for, but you can compute arbitrary accuracy. The claim to fame of this number, in addition to being a critical exponent of this 3D CFT, is that it's bigger than 1/2. So this is, this is the unitarity bound, and it's obeyed by this. Delta 2, which is equal to R2, is 0.708235, and you can. And again, it's bigger than 1/2. And if I haven't messed it up, twice times this number plus this number should be 2, or very close to 2. Okay? And if I have messed it up, you go home and you do this on Mathematica and find the correct numbers. Okay? Now, I've computed these R charges, which fix the dimensions of many operators in this IRCFT. Moreover, I can put these numbers back into F and evaluate F of R1 and R2 at these extremal values, if you wish, at these conformal values. Okay? And you find some answer. Again, numerical approximation. Notably, this answer is smaller than twice times F of 1/2. So in the UV, I have two free chiral superfields, and their free energy will be, each of them will be, will have a free energy which is, yesterday I told you that this is 1/2 log 2, right? So this is the free energy of the UV theory, and this number is the free energy of the IR theory. And this is a consistency check of what I told you should be a theorem, this F theorem. Okay. Is that clear? Okay. So, homework assignment. Take this superpotential, and of course, the Kähler potential will be canonical. So now take 3 chiral superfields. and compute R1, 2, 3, the superconformal R charges, and then compute the sphere free energy of this model, just to learn how it works. Okay, any questions?
Yeah. Yes, sorry.
Yeah, someone is
asking
a question here, so maybe people online wait a little bit. Sorry. What was the question? Sorry. So the question was if f, is it possible that f doesn't have a maximum? Yeah, I guess. Well, I haven't seen an example. I mean, f is this nasty function. If you have a chiral superfield, it's this function of little l. Maybe you can analyze it and see that it always has a maximum. So I think for that case, you can actually see and analyze it more rigorously. But in the case when you have gauge fields around, I'm not sure how to prove that it always has a maximum. So, well, in some sense, this F theorem should guarantee that. But yeah, I don't have a good argument in the general case when I have gauge fields. Right. So yeah, good. So Davide is emphasizing an important point that here I am making an assumption that this RG flow will have this form, meaning that the IR theory will be conformal. And maybe one way for this to not have a maximum will be if this is not a conformal theory, but something like a confining gapped model. There's other issues with this, small subtleties, let's not call it issues, which I will emphasize a little bit later today. So there are some asterisks and footnotes and so on. Yes, online there was a question?
Yes, sorry. I would like to ask, maybe I missed something, but I don't understand why we should maximize and not minimize the free energy, since during the RG flow, the free energy gets smaller. So I don't know if I missed something.
Yeah, well, there's a simple answer, ask Dan. But yeah, I mean, you really, so in this paper which I mentioned of Closet, Komargotsky, Festucha, Dumitrescu, and Heiberg, they really show it has to be a maximum. But you're asking something about an intuitive, yeah, I cannot on the spot give you an intuitive reason why it should be a maximum.
Okay.
Yeah.
Okay. It's not trivial. Okay.
Right. I mean, yeah. So at the moment, this sounds like a prescription, and as I said, it has been analyzed in more detail in this paper, and it should be a maximum. Yeah. But
okay.
I can't say much more. All right. So at this point, you have this nice result. So you can use this localization method to compute the R charges for, in a sense, infinitely many CFTs, strongly coupled, and so compute exactly the conformal dimensions for them. If this was the whole story, it would be a nice story, but maybe not so exciting. I don't know. I think it's exciting, but yeah. But actually, that's not the whole story. So this method of SUSY localization can actually be applied when you start switching on deformations. So again, to remind you, this was the vanilla case where the path integral had no insertions, nothing was deformed. The only thing that appeared in the path integral was the choice of the gauge group, the representation of the chiral multiplet and these R charges. That was the full story. Now, I want to start doing more interesting things. So add sources to the QFT and see how things change. This is what every physicist should do. Give the system a kick and just wait and see how things are going to dissipate or whatever. Do some physics, right? So now let's study deformations. So one thing that you may study is deforming the metric on the sphere, squashing it a little bit. Why is this a good idea? This is nothing specific to supersymmetric quantum field theory. In general, we know that the energy momentum tensor couples to the metric. So there's this natural coupling. If you have a Lagrangian of a QFT, you can add a coupling like that. Okay? So a coupling, so if I switch on a source, so the metric is the source for the energy momentum tensor. The energy momentum tensor is this universal operator in every QFT that knows how much energy and momentum are in the system. Seems like an important gadget. So now, if you put this, sorry, this should be S QFT. So you start with a Lagrangian of a QFT, you add this, and if you do this in the path integral, you can add this, differentiate with respect to G, the partition function, the path integral, and then put G to the identity, the flat space metric, and this will give you endpoint functions of the energy momentum tensor, right? So T mu nu, 1 to n is schematically take n derivative of the path integral with respect to the metric. Well, indices don't work here, but okay, you understand what I'm saying. You know, I have to do it n times, and then put the metric to be the flat one, or the reference metric. So this is a QFT with respect to some reference metric G0, and this is a perturbation. Okay, this is how we do quantum field theory. This is why we can say that the partition function, the path integral in the presence of sources for the quantum fields is a generating functional for endpoint functions. These words hopefully sound familiar to some of you, or to all of you, hopefully, okay? So this kind of little digression on QFT motivates us to study the deformations of the round sphere. So the round sphere is a conformally flat manifold, so it's suitable for studying CFTs, but if you want to move away from the conformal point, or if you want to study correlators at the conformal point, endpoint functions, you better give the sphere a kick a little bit with some squashing, differentiate with respect to the squashing, and put the squashing to 0 or to 1 in this case. And then you will learn about endpoint functions of operators. So in this language, what we've computed here is the expectation value of 1, right? So this f of S3 was the path integral without sources. That's why it gave us numbers, not functions. Is that logic clear? Okay. So now we want to move from the 0-point function to endpoint functions, or 2-point functions at least. That's our goal. Okay, so the parameter omega, for various reasons, can be rewritten like this. This is 1 over b. Anyway, so when b is equal to 1, you get back the round S3. And when b is not 1, you have a squashing of the metric. So for B equals 1, the round S3 has SO4 invariance. When B is not equal to 1, you break that to SU2 times U1. How do you see this, SU2 times U1? Well, I have a big, nice two-sphere here. This is S2. The isometry of S2 is SO3 or SU2. And then I have a U1, this dd psi killing vector. That's kind of how it works. Okay. So I'm doing a mild squashing of the sphere that keeps a lot of isometry. And what's nice about this story is that there's still a killing spinner. There's still this nice spinner that obeys this equation that I started with yesterday. So this is in some sense a supersymmetric manifold, how to say. It admits a nice spinner, so I can hope that I can put a supersymmetric quantum field theory on it. And indeed, you can do that. So the Lagrangian that I wrote down yesterday has a generalization where B is not equal to 1. Right? So the Lagrange, the big thing that I was writing on multiple boards yesterday was for B equals 1. And I claimed that you can just add arbitrary B in there through some modifications. I'm not going to write it out explicitly. Then you have a supersymmetric Lagrangian, which depends on B. And the additional nice thing that happens is that this whole SUSY localization argument goes through, and then you find an expression for the partition function or the path integral of the theory on the squashed sphere. Okay? So this is nice. I'm not going to write down the full thing with the gauge field. I'll give you the answer for a chiral superfield. So only, the simplest case. So you find that f as a function of the squashing and of the R charge. So this is for chiral superfield. We find this expression. Two, 1 minus R. Now you kind of see how this B appears. Okay, so now, 0 to infinity, sorry. So what did we do here? We turned on a source for the metric. We turned on a non-trivial metric on S3. So for B not equals to 1, this theory cannot be conformal. Okay? The isometry group of this is not big enough to have conformal invariance. So this is the free energy of a non-conformal theory as a function of B. This is a full nonlinear statement, meaning B can be as big as you want. For instance, 1000. Doesn't matter. This formula applies. And so this is the full generating functional for correlation functions, for connected correlators of the energy momentum tensor. So at this point, you should be really blown away because this is a non-perturbative statement, okay? Okay. So now I will follow this logic here, and I will compute endpoint functions of the energy momentum tensor. So the 1-point function of the energy momentum tensor should be 0 in a CFT. So this should come out of here. So you should go and calculate the first derivative of this with respect to B, put B to 1, and you should find 0. And if you don't find 0, quantum field theory is wrong, okay? So this is a very dramatic check, but of course it's true. So that's your homework assignment. Take this integral and do that. So this is the 1-point function. The next simple thing is the 2-point function. This should be somehow related to TT, the 2-point function of the energy momentum tensor. One thing that's important here is that somehow these correlators come integrated over the sphere. So I don't really compute the full correlator, I compute this thing integrated over S3 and contracted with the metric twice. So this is the kind of price that you have to pay in this analysis, is that you don't really get the full dependence on space-time of the correlator, you just get the coefficient if you wish. But the dependence of space and time on this is completely fixed by conformal invariance. I wrote a formula for you. Remember, at some point, I was writing this type of equation. It's equal to CT and then some P tensors, right? 1 over x square. Remember this? So now I claim that this thing computes the integrated right-hand side. But the integrated right-hand side is proportional to CT. So you just have to work out the integral of this quantity. It's some pi's and 2's and so on. And then you will compute CT with this method. And CT was anyway the dynamical information in the theory. The thing that is not fixed by the conformal symmetry. So people, of course, did that. And you find that CT is 48 over pi square So again, this is a non-perturbative statement. This is an exact answer for the 2-point function of the energy momentum tensor. So the logic is you start with the QFT that you want, put it on a round sphere, then squash the sphere, compute the path integral, then differentiate it twice with respect to b, find an answer, put b to 1, multiply it by 48 over pi square, and you get CT. At this point, you've computed a dynamical quantity in the conformal field theory. You've done this through this roundabout way with localization, S3, squashings, blah, blah, blah. But once you know CT, it controls the 2-point function of the energy momentum in flat space. What I wrote here is the 2-point function on R3. So the magic is that this free energy on S3 allows you to compute quantities in flat space in this very roundabout way. So someone asked me, why don't I do this in flat space? Well, for various reasons, but this knows about correlators in flat space. This is an important conceptual thing. So if you have some kind of existential questions in your head, it says S3, I don't have a Hamiltonian, I don't have time, you know, physics is about things changing in time, that's what I signed up for. You know, think of all this as a machine to compute. Don't think of it as some physical thing, if you want. If you're really bothered by this lack of Hamiltonian and time, yeah. Once you compute this, you found a 2-point function in flat space. Okay. So now, this by the way, is valid for general 3D n equals to 2 CFTs. Okay. So here I've written the answer for a chiral superfield, so I've removed the gauge fields, but this kind of a statement is valid more generally. Okay. So in our example for a chiral superfield, there you get this. You get a nasty integral, for me at least, and I come from Eastern Europe, I'm supposed to know how to do integrals, but I don't. So, you know, my heritage has been violated here. So this one is a really not a pleasant one to do. But of course, Mathematica will happily do this for you numerically once you fix R. So R is the R charge. So the only thing that you don't know is the R charge. Okay? So the logic is the following. Start with some QFT that you're interested in. For instance, this one, which is on your homework. Okay, that's a good QFT. Then compute the free energy on the round sphere as a function of the R charges. Maximize it, find the maximum. That will compute the R charges for you. And then, with these R charges, I have a formula for much more. Not only for the dimensions of some operators, but I also have for the 2-point. So I just have to put R here and compute this integral. Is this clear? So I'm slowly starting to use this tool to extract exact information, not only about the spectrum, but also about endpoint functions. So, you can, of course, do this for any R. So you fix R and you ask Mathematica to compute this integral. Sometimes it takes nice values. So CT for R equals 1/2. That's the free theory, right? I saturate the unitarity bound with this, and I get 6. Okay, this will come out of this integral. And it can also be computed independently from just starting from a free, free theory of 2 scalars and 2 fermions, writing down the energy momentum tensor, writing down a 2-point function, and start doing contractions, just like, Gaussian stuff. And I'll get 6 in this normalization that I'm using. Okay. So the more interesting story is the Wess-Zumino model. So this is our friend, the critical Wess-Zumino model with 1 chiral superfield, right? And this one, you really have to work hard to solve this integral. And some people did it, not me, unfortunately. This is the answer. This is an exact answer. And you can write an approximate numerical value for it, which is this. And at this point, you should go back to, I don't know, the whole week is a fog in my head, but let's say Wednesday or something. I told you about the conformal bootstrap, right? I was making this plot with the kink, and I told you that we can zoom in on this kink and start extracting the 2-point functions and the dimensions of operators. And I told you that CT from the bootstrap came out to be this. So, point made, I think. Yeah, so this is the exact answer. And this is this approximate bootstrap method. So this is another evidence that this kink that we have identified from the bootstrap is actually the correct point in theory space, so to say, which is the critical Wess-Zumino model. Okay, is that clear? Is this logic clear? Yes? because the theory is conformal. This operation going from flat space to S3 is allowed when you have a conformal theory. Yeah, so this expression is going to change on S3. It will look different, right? There's an expression on R3. You should write down an explicit stereographic projection from R3 to S3. If you don't know how to do it, Wikipedia knows. And then yes, you have to, yeah, you have to do some work to rewrite this on S3. But because this is a conformal field theory here on the left-hand side, it's bound to work. Just to warn you, when you do such operations, conformal mappings, if you are in even dimensions, which we will talk about in an hour or so, you have to be very careful because then there's a conformal anomaly. And so this transformation is actually kind of subtle. But we're in odd dimensions and things are nice and it just works. Yes? Yes. Yes, so you have to. The energy momentum tensor of the CFT is traceless, yes. But I'm deforming slightly away. So this G here, this G that I'm contracting, think of it as G0 plus some H mu nu. And so that's what's gonna give us. So this is actually contraction with H, with the perturbation. Does this? Yeah. Exactly. So yes, I'm giving the system a kick by squashing a little bit the metric. That breaks the conformal invariance, gives me non-zero stuff. Then I extract what's the non-zero stuff, and then I put the perturbation to 0. That's the logic. Just like when you have a CFT and you want to, let's say I have a 3-dimensional CFT and I have a dimension 2 operator. What would you do? You would, in the path integral, you add a source for the dimension 2 operator. And then, if you really add this source and keep it non-zero, you will undergo an RG flow and you'll change the theory. But the trick is to add the source, differentiate with respect to the source, and then put the source to 0. And this operation computes correlators in the conformal theory. But that's what I'm doing here. Yeah. So, in some sense, yeah, this is non-zero because this is the perturbation away from conformality. Okay, anyway, if you should sit down and work this out. It's not so hard. It will give you intuition how things work. Okay. So now, let's keep on doing this for 15 more minutes. Let's study another deformation, so the energy momentum exists in every QFT, every local quantum field theory obeying whatever the Weitman axioms, blah, blah, blah. Every reasonable QFT has an energy momentum tensor. So this is kind of a universal thing to compute, CT. Now, you may or may not have global conserved charges, symmetries, but if you do, assume we have 3D n equals to 2 CFT with a U1 flavor symmetry. So, okay, not every CFT will have that, but if you have it, then there will be a current for that. There will be a conserved current according to Professor Noether. Okay. That current is an operator in the quantum field theory, and you should be asking, what is the two-point function? The two-point function is fixed by conformal symmetry with some normalization conveniently chosen so that when you do integrals, things are nice. So this p mu nu is this operator with two derivatives I was writing down, right? D mu d nu, and then delta mu nu d squared with some coefficients. I don't have it here, but it's the same one that we used for the energy momentum tensor. This, the form of this, p mu nu, is fixed by the conformal symmetry. So again, the dynamical information is in this Cj. So this Cj will depend on the CFT at hand. Everything else is fixed. This operator, if you have n equals to supersymmetry, lives in this multiplet. Right, so you have this multiplet that I was writing down on Monday. I will write again. So it starts off with a scalar field of r charge 0 and dimension 1. And then there's the bottom components are a scalar field with dimension 2, and then the current, a spin 1 dimension 2 guy. Okay. So now you should remember the vector multiplet I was writing yesterday. I was writing things like this. Let's be more explicit. Right, this appeared in the Lagrangian yesterday. Well, map this to this, right? This is not an accident that these two things are the same. This is sigma, this is d, this is a mu. These are the lambda minus and the lambda plus. Okay, so in particular, this is the thing that couples, so there's a coupling in the Lagrangian between a gauge field and a current, right? So this is the analog of how I was coupling the energy momentum tensor to the metric. So turning on the metric switches on powers of the energy momentum tensor. Turning on a background gauge field will switch on powers of this operator. Okay. Sorry, I was not very pedagogical. I forgot to say something. So this two-point function Ct is the two-point function of the energy momentum tensor. But with equals to 2 supersymmetry, the energy momentum tensor lived in another multiplet like that started with a spin 1 current. That spin 1 current is the U1R symmetry. So I have an analogous multiplet like that. Sorry. So I have this multiplet. The R symmetry, two supercurrents, as they're called, and the energy momentum tensor. So this is now due to supersymmetry. So Ct is the two-point function of this guy, but because of supersymmetry, the two-point function of this operator is related to the two-point functions of all these other operators. These are called supersymmetric word identities. When you have a symmetry, you can act with a symmetry and relate correlation functions. This is the quantum field theory analog of the Noether theorem. So the two-point function of this J mu r can be called, let's say, CR, right? CR and CT are two numbers that in a non-SUSY QFT will be unrelated, but in a SUSY QFT they are related. So this coefficient is explicitly known, but I didn't write it down. It's an order 1 number. Okay, so it's like this. So it's something like whatever, 3 over pi square or something like that. So when you compute this, you have computed already this. Okay. So the same logic can be applied also here. If I'm interested in computing Cj, It's a two-point function of the current of this member of the multiplet. I can extract Cj from any other two-point function in the same multiplet by carefully using supersymmetric word identities. In particular, I can compute the two-point function of this operator, which is a scalar operator, so things are a little bit simpler, and out of it extract the two-point function of this operator by acting with the supercharges, basically. So, how do I compute the two-point function of this operator? Well, this operator is a scalar. It will have a coupling. I switch on the coupling. We differentiate with respect to the coupling twice and put the coupling to 0. So, and if I do it for this one, this will give me the answer for this one. So this can be done because this sigma also appeared, if you go back yesterday, that the path integral was of on the round sphere now. So I'm back on the round sphere. I don't want to be turning sources for the energy momentum tensor, but I want to be turning on a source for this guy. And that guy was literally called sigma in the Lagrangian yesterday. And so actually on the round sphere, we had an expression as a function of r and sigma. A few things were called sigma yesterday, sorry. Let me call this m. This was this thing that I called real mass that appeared in the combination like this. Okay, so I'll call it m now. It acted effectively as a mass term. Okay. Sorry, where was I? Yes. So the answer for this was minus L, 1 minus R plus I M. So again, if M is non-zero, you have a non-conformal theory. So R, you fix to the supernormal value by doing this F maximization, and once you do that, this parameter M describes a relevant coupling for a dimension 1 operator with this operator. So it will trigger an RG flow if you turn it on and keep it non-zero. What we do here is, again, slightly different, as I emphasized. We turn it on, differentiate twice with respect to it, and then put it to 0. And so the claim is that this number Cj is this. Okay? And again, this is a statement. So this expression above is valid for chiral multiplets. This expression is valid in general, gauge theories and so on. So this is the content of this supersymmetric word identity I told you about, which is valid for any 3D n equals to 2 CFT. Okay, to not be too abstract, let's go to an example. And it's again our friend. So we have had a few friends this week. One of them is this XYZ model. And I already told you that it has a flavor symmetry. So the charges of X, Y, and Z, the R symmetry charges were 2/3, 2/3, 2/3. And then the U1 flavor charges are 1, -1, 0. Okay? So this is all I need for this equation. R are the R charges. These are, if you wish. Sorry, I had to put here sorry, this is the flavor charge. Because how much, this is a source and this is how much a field will fill that source. So for instance, this field will not fill it at all. Okay, so I use this formula. find at f of R, well, I have 3 chiral superfields, so I have 3 terms. I have to just add up the result. So 1 minus 2/3 is 1/3, so I have 1/3, 1/3, 1/3. And then the q's are here, 1, minus 1, and 0, so I get 1 here, minus 1 here, and 0 there. So that's my free energy in the presence of the source for the operator sigma, this m. And, well, I compute Cj by 2 derivatives, whatever, 2 pi square, this f, and you find 16/9 minus 4 pi square root of 3, which is approximately 1, but not exactly 1. So this is for xyz. If you do it for the same field content, but without a superpotential, so for the free theory, you get 1 in this choice of normalization. So that's one indication that you don't have a free theory. You have some interactions. Okay. Yes. So I'll stop with these examples, and I'll have some comments to make. But before that, any questions? No? Okay. So I've tried to illustrate here on these examples that are relatively simple the power of this SUSY localization method. It allows you to compute dynamical, strongly coupled information for 3D n equals to 2 CFTs. General CFTs, we've focused on chiral superfields just so that we keep things as simple as we can, but this applies also for gauge theories, which are more complicated. And it allows you to compute some part of the spectrum of anomalous dimensions for which operators? For the supersymmetric invariant ones, these short and semi-short multiplets. And it allows you to compute some correlation functions, right? Again, which ones depends on supersymmetry. For instance, when I was doing the squashing of the sphere, I chose a very careful squashing that preserves the spinor, that is compatible with the supercharge. If I choose a random squashing of the sphere, sure, that's a thing that you may want to compute, but the method of SUSY localization will not allow you to do so. So the logic is that you have an answer on the round S3 for the conformal point, and then you identify sources, deformations, that are compatible with some of the supercharges, and for those you can hope that you will find exact answers. And this is true for local operators, as I showed you, this spin 1 operator or the spin 2 operator, which is the energy momentum tensor. But it's also possible to do for non-local operators. So things like Wilson lines. You can also have a supersymmetric version of a Wilson line. And if you insert that Wilson line on a nice part of the sphere, for instance, equator, then you can prove that that is invariant under supersymmetry, and then compute the expectation value of that Wilson line, if you so want. Okay, so the method is very general, but you have to be careful because it's not really applicable to all observables. It's applicable to some subset that are, in some sense, invariant under supersymmetry. Okay, another useful application of the method, if this was not enough, right? sorry, one more comment. I told you about this magical thing that you can start with two different Lagrangians for an asymptotically free quantum field theory, and then somehow they can flow to the same infrared CFT. Right? This sounds a little bit strange, maybe. But if you want to check that, well, you can start with the two different Lagrangians in the UV, use the method of supersymmetric localization, if you wish, twice, do two independent calculations, and these two theories are going to flow to the same CFT. The answer should be the same. Okay? So, for instance, I told you that this XYZ model is equal to supersymmetric quantum electrodynamics. So, then, if you don't believe that, you can go and compute the path integral in both of these theories. It will look very different because in one of them I have to do the nasty integrals over the gauge group and so on. In the other one I have this function little l. The answer is written up there. And you have to work and show that these two answers are actually the same. And they are. They're not obviously the same when you write them down. So this is the simplest example. This XYZ and quantum electrodynamics is the simplest example where this method can be used to prove dualities. Again, it's not a proof, it's just more evidence that the theories are the same. But you can actually do this for much more fancy examples. And this has been a little industry, people revisiting some claims of dualities between certain theories and trying to establish them more rigorously. And then, as you do that, you find sometimes you find amazing identities between special functions that even mathematicians are surprised by. So, because you have a very different rewriting of the partition function for the two different Lagrangians, and physics informs you that these two different expressions must be the same, and if you have sufficiently complicated examples, these are very nasty special functions. And so in some cases, especially in four-dimensional n=1 quantum field theories, this has led to new identities between special functions, elliptic gamma functions and so on. So it's even has applications in some obscure branches of mathematics. Okay. So now I want to emphasize another point because Maldacena and Witten and Gubser, Klebanov and Polakov wrote an amazing identity, right? This is a fundamental identity of science, and it is true, right? So it is true, but you have to say what Z is. And at this point, I hope I was not recorded. I hope you have seen the movie Pulp Fiction. There's a character there called Z. Anyway, invent a joke based on this. Where is Z? What is Z? Z, on one hand, is a path integral with sources for a quantum field theory. This is the left-hand side, let's say. And on the other hand, it's supposedly a path integral of a string theory or an M theory. Right? This is ADS CFT or gauge gravity duality or holography, right? It's about Z. So now, with these tools from the quantum field theory, I have a powerful tool to compute Z. And yeah, maybe you may want to apply this tool to this identity. And indeed, this is a productive enterprise and an important one, I think. So I don't have time to go through the details, but I told you about M theory, so I will use an example from M theory. There's these gadgets that are called M2 brains. Okay, these are extended objects with 2 spatial and 1 time dimension, so this is some kind of a 3-dimensional object. At low energies, you find a quantum field theory that lives on their world volume. And this theory has a name. It's not a very inventive name. It's the ABJM theory, or again, Bagger, Gustafsson, and Lumber theory. So these are Aharoni, Bergman, Jaferis, Maldacena. Okay, so this theory arises from putting n M2 branes. So these are extended objects. You pile them up like this. You make them coincide, and you put them to live. The orthogonal space is a cone over S7. So that is a smooth space. It's called C4. It's the, or R8. Okay, it's flat space. So that's the orthogonal space, and of course their word volume is 2 plus 1 dimensional flat space. So 3 plus 8 is equal to 11, which is a good number. That's where M theory lives. Okay, so actually you can do a slight modification here. You can have an orbifold, and this orbifold action is a very specific one. It's actually smooth. So there are smooth cones like that. Okay? Good. So according to this famous identity, you're instructed now. So this is, if you wish, the picture in terms of branes. This is the fundamental science. And then the applied science is to take 2 limits of that picture. One limit is the QFT limit. Go to the low energy in physics on the word volume of the brane and extract a quantum field theory. This is this quantum field theory. And the other limit is turn on the graviton, make this a space, which is now a flat space, curved, and see what happens. What happens is that you have an ADS solution of 11-dimensional supergravity. ADS 4 times S7 mod ZK. And so these 2 things should be dual to each other. Z should be equal to Z, where Z of the left-hand side is the path integral of this. Z of the right-hand side is the path integral of M theory on this space. Okay, we don't even know what M theory is, so the path integral of M theory is, voodoo. So we don't know how to compute that. But this guy is a 3-dimensional Chern-Simons matter theory with some specific field content. So I just told you how to compute such things. Exactly, right? Not a approximation, exactly. So in some sense, with these tools, you have a method to compute this object. And if you believe this identity, this essentially defines for you the path integral of M theory on this space with some careful words that you have to say, right? But that's one application that is somehow goes in the direction not understanding quantum field theory, but understanding actually quantum gravity, which is a very obnoxious thing to try to understand, but we try. So this theory, I'm not going to write it down. This ABJM theory is UN at level k times UN at level minus k. So these are the Chern-Simons levels, the gauge group. So I have 2 gauge fields. And then there's 4 chiral superfields, annoyingly called A1, A2, B1, and B2. These are 4 chiral superfields, and there's a specific superpotential. These fields, A, are in the fundamental representation of this gauge group and in the anti-fundamental of this. And these guys are vice versa, fundamental of this and anti-fundamental of this. These theories are called quiver. This kind of construction can be summarized by what's called a quiver diagram, where the circles, the nodes of the diagram encode or represent the gauge group. So here is U1K, here's U1 minus K, and then these are A1, A2, B1, and B2. The arrows represent the matter fields, the chiron multiplet, and when they go from this node to this node, it's fundamental here, anti-fundamental here, and then vice versa. Anyway, this is a specific model with a specific Lagrangian written down by A, B, J, and M. And so you can apply SUSY localization to it. Okay. And amazingly, this path integral is computable. Okay. One thing that I haven't told you, but you should know, half of you said the words holography in your gong show, so you know. How this thing works is that there's a parameter n here, the number of branes, right? So for the weakly curved gravitational description to be valid, G Newton has to be small, which translates into n being large. So actually in M theory, for those of you who know, things are simpler than, let's say, for ADS5S5, because in n equals 4 Young-Mills, I have two dimensionless quantities, roughly, n and then the gauge coupling, which in string theory map to alpha prime and GS. I have two couplings in a string theory, right? In M theory, I don't have a coupling. It's such a fundamental theory that it doesn't even have a notion of a coupling. It's just a thing. It's like a Kandinsky picture. It's like, what have you done to art, right? You know, so that's what M theory does to physics. We don't know. But we know that the large n limit of the gauge theory should be the weakly coupled limit of the gravitational theory. So I have to compute this path integral at large n if I want to access 11-dimensional supergravity. And this can be done. So for instance, if you don't have any sources, this is the vanilla answer at large n. And then you can keep on going. There's an n to the minus 1/2 term with some coefficients, and then it's an infinite expansion in n. So this comes out of the field theory. And on the gravity side, these should be things that you can compute in M theory somehow. The leading term, the n to the 3/2 term, should come out from evaluating the class. This is, if you wish, the classical 11-dimensional supergravity term. So it comes out relatively easily by evaluating this is a solution of 11-dimensional supergravity. You put this solution back into the Lagrangian and evaluate it. This is the on-shell action, as it's called. You have an action of M theory. You have a solution of M theory. You compute this on-shell action. You have a map between G Newton and n, a parameter n. So the dimensionless ratio is the scale of ADS, something like this, L square over G Newton, has the right units. And so this is somehow mapped to n. And that gives you the first term. And it works. And in fact, it works for a large class of such manifolds, for a large class of such cones. There's a whole little industry here that you can spend your life on, basically. But the point is that that's only one term. These other terms should come from somehow quantum corrections to 11-dimensional supergravity. And that's a hard thing to compute because quantum corrections to string theory, at least we have a string theory. You know, they're hard to compute, but at least you know alpha prime, GS, you can draw pictures, loops, and so on. In M theory, we somehow don't have a fundamental microscopic understanding of the theory, so even it seems very hard to ask what are the quantum corrections to M theory in general. And so this gives you answers, and then you can try to hope to be able to somehow extract information about M theory from them. And so this is another very useful, I think, application of the SUSY localization methods to apply to large N gauge theories with holographic duals. And then it's really not anything fluffy. You get equals and square root of 2 and so on. So you really have to find a way to compute these numbers from N theory or use them to extract information. When you apply the same logic to other curved manifolds, so one thing I should have said is that this SUSY localization method is actually applicable to many compact curved manifolds. So for instance, things like one famous example is S1 times a Riemann surface. You have to say now, this is a curved space. You have to carefully study the Lagrangian of the theory on that space, see what is the supersymmetric Lagrangian. People have done that. And so now you can ask, what is the path integral on this space? And there is again some SUSY localization formula, which you can write down and try to evaluate the free energy, the logarithm of the path integral on this space. Okay? This now has a circle. So it has a Hamiltonian. The circle is something like this should schematically something like a partition function, a trace over the Hilbert space. This thing should be counting states somehow. Which are the states? These are the supersymmetric operators in the theory. So this is a counting function that you can in principle compute exactly. And you can say, okay, very good, I'm counting operators, but I didn't sign up for that. I wanted to be like Stephen Hawking. I want to understand black holes. So this is the thing that should even beat Stephen Hawking, because this thing has an expansion at large N that looks like this, with some different details. And so the leading term of this guy will be the Bekenstein-Hawking entropy. The subleading terms will be the corrections to that, the quantum corrections to the entropy. So that's another powerful application in the context of quantum gravity. Yes? Yes. So this is a glorified Witten index, yes. It counts only the supersymmetric ground states, right? Which is why, essentially, you can compute. If you want a thermal partition function, you have to put anti-periodic boundary conditions, roughly. There's some subtleties. But anyway, you have to put non-supersymmetric boundary conditions for the fermions, and this will give you the partition function, the actual partition function, and that computing that for a strongly coupled quantum field theory is an exercise left for the reader. That's not something we know how to do in general. But so this indeed will teach you about the microstates or the counting of the microstates of a black hole, but not any black hole, supersymmetric black hole. So so you still don't fully beat Hawking, but a little bit. So yeah. It's a good point. Yes, logs are annoying. Yes, sorry, I always forget that people are watching online. So yeah, the question was about why do we have a log here? The naive thing looks like powers of G Newton, right? So these things will be mapped to powers of G Newton, and I have some higher derivative expansion of this 11-dimensional supergravity, and so on and so forth. The log comes from the fact, again, roughly speaking, I'm oversimplifying, is that on this space, right, this is a classical solution of GR, there are massless modes, or low energy modes, let's say, that can run in loops. So this is, if you wish, from the quantum field theory of those modes, those excitations around ADS4, S7, that are, scalars, vectors, spin 1/2, spin 3/2, and so on, the metric. All these modes can run in loops, and those loops are controlled by the G-Newton coupling, like the vertex somewhere is G-Newton. So, and then you get a log of the coupling, and that's this log. So this log comes from, so there are two types of quantum effects. One is your Wilsonian effective action, your low energy effective action gets higher derivative corrections from irrelevant operators. That's the QFT way to say this. So the microscopic formulation of M theory, which we don't know currently, will, when you take the G Newton to 0 approximation, you have an expansion in higher derivatives of the metric and all other fields. But then you also have these things that can run in loops, and those are also quantum corrections. Those can be, those are the two things that control this large N expansion. Schematically, yes. Other questions?
I have another question.
Yes.
It's on the theory that is on the M2 brane. I cannot really, I don't really know what the excitations are on the M2 brane. The theory on the word volume of a D brane, I can kind of understand as excitation of open strings, but on the M2 brane, I mean, in M theory, there are no strings, so I'm confused.
Yeah, so you're in very good company because no one knows what the excitations of the M2 brane are, right? So this is what I was emphasizing. We don't have a fundamental formulation of M theory, so somehow it's hard to derive this theory. So in the usual D-brane story, you have D-branes with flat word volumes and open strings, and then in flat space, you can go through the motions and compute the spectrum of the open string with Dirichlet boundary conditions, and you find massless gauge fields and some other excitations at the end, and they organize into multiplets of supersymmetry, and this is how you derive that, let's say, on the D3 brane word volume, you'll get n equals 4 Yang-Mills on the nose from the open strings. Because we have a formulation of the microscopics of type 2B string theory, at least in flat space. Now here we don't. And so you have to be smart to argue or to find this theory, and it took quite some time. So this is a paper from 2008. So it took, let's say, from 95, Porchinsky understood D-branes to 2008. It's a bit of time, right? Yeah, so it's not easy, and in fact, you cannot really derive it. You can argue for it using dualities in string and M theory, because M theory on a circle should be type 2A string theory, which is T dual to type 2B string theory. So in this paper, there's some plausibility arguments using that chain of dualities. And another argument is actually this correspondence, holographic correspondence. So in some sense, this you can view as a evidence or a strong evidence that this works, because the leading term in this large N expansion matches. So for instance, you should be bothered by the power of 3/2. So this was a big mystery of science. You should be starting for something. I mean, ordinary gauge theories have n² degrees of freedom. They're n by n matrices, right? For SUN gauge group. So how can you have n to the 3/2 scaling? This sounds crazy a little bit. So something should, something it should give. So notice that this is k to the power 1/2, and this is n to the 3/2. So this is the M theory limit of the answer. So how do you get type 2A? Type 2A, I should be getting ordinary gauge theories with n² scaling. Well, the type 2A limit is actually k has to scale as n, and then k to the 1/2, n to the 3/2 will give you the n² term in 2A. So everything is consistent with what we know about string and M theory. But it is not a derivation like the open string story. So it's harder because M theory is harder. I hope this somehow answered the question online.
Yes, and is it the same story for the mysterious theory living on the M5 brane?
Yeah, that's an exercise left for the reader. We don't know how to do that yet. So there's some ideas, but yeah, it seems to be much harder. But Omar is going to solve the problem. we have a student. He's not here again. He's solving the problem probably. Anyway, yes, no. M5s are harder. M5s have n cubed scaling of the degrees of freedom. So n to the power 3. So something dramatic should happen, and there's various ideas and speculations about what happens, but we don't have as detailed answer as what is on the board here. Other question? Yeah. No, when you compare fundamental strings, I get fundamental strings. Yeah, so there's bells and whistles here that are important. So this, yeah, you cannot really do this limit that you're describing here, because this is not some kind of flat space compactifications. There's some details what happens on this S1. There's some flux on this sigma G. There's a Wilson line for a background tower symmetry, and so it doesn't allow you to do this limit, at least as far as I know, this limit in an obvious way. Yeah. But morally speaking, you can ask, and this is really some open question, and I've asked myself, is there some string theory that, is there some limit where you can kind of erase this and think of this as a worksheet of the string and try to compute some genus expansions of strings and compute that? Yeah, but this is very fluffy. I don't know what else to say. On the face of it, doesn't seem to work. But maybe there is some clever way of doing it. Yeah. All right, any other questions? Good. So I'm basically done with the SUSY localization stuff, unless there are questions. I have probably about an hour to talk about anomalies, depending on how much you interrupt me with questions about M5 branes, but yeah, roughly an hour. But if you want, we can have a break now a little bit and then continue, or is this, organizers, is this allowed? Is this legal? Okay. Okay, so let's, 15 minutes, is this okay with everyone? Yeah, okay, 15 minutes. So people online, go and have a coffee. Or a whiskey if you are in Australia or something, I don't know.